Hey, welcome. So today we are diving deep into one of the most important ideas in all of artificial intelligence, and that is search. Now hold on, I'm not talking about typing something into Google. This is totally different. We're talking about how an AI system explores this huge invisible world of possibilities to find just one single solution. Whether that's finding the perfect unbeatable chess move, or a brand new drug combination that could save lives, or even just optimizing a delivery route for a fleet of trucks. But to really get our heads around it, let's start with a problem that you and I deal with pretty much every single day.
Really think about it for a second. When you open up your map app, it doesn't just know the best way to get to work. It has to find it. In just a couple of seconds, it considers thousands, maybe millions of potential paths. It's looking at real-time traffic. It's checking for road closures. It's thinking about turn restrictions, speed limits, the whole shebang. And it does all of that just to give you that one single, beautiful blue line on your screen. So how does it do it? Well, it's performing a search. And the powerful ideas it's using are the exact same ones we're going to break down right now.
And this right here, this is the big idea we're going to unpack today. This little phrase separates the entire world of what's possible, every single road in the entire country, from the specific process of actually finding a route. And AI doesn't see the whole map all at once. Nope, it builds a journey one choice at a time, exploring possibilities as it goes. If you can really grasp this key difference between the static landscape and the dynamic exploration, well, you've got the key to everything else that follows.
All right, let's get into it. Here's our roadmap for this little explainer. First up, we're going to dig way deeper into that whole map versus journey idea. Then we'll learn the lingo, the essential vocabulary of search, states, nodes, and frontiers. After that, we'll look at the 4 crucial tests that we use to figure out which search strategies are actually good and which aren't. And then we'll pull back the curtain on a universal recipe that pretty much powers all of them. And finally, we'll face the real-world problem, the big dilemma that every single AI engineer has to deal with when they try to put this stuff into practice.
Okay, so let's tackle our first big concept. When we're talking about search, we have to be super precise about what we're searching through versus what the actual act of searching looks like. I know they sound kind of the same, but in the world of AI, they are two totally, completely different things.
So this slide here just nails that core difference. On the left, we have what's called the state space. I want you to think of this as the complete, totally abstract map of every possible situation. For your GPS, a state is a physical location, right? Like an intersection. For a chess AI, a state is the exact position of every single piece on the board. The state space contains all the possible board positions, which, by the way, is a number so huge it's hard to even imagine. It's this giant, theoretical thing that exists all at once. Okay, now look to the right. That's the search tree. This is not the whole map. This is the journey being built, live, in real time. Picture starting at your house. The algorithm thinks, okay, from here I can go left or I can go right, and boom, each of those choices creates a new branch on this tree. The map exists, but the journey has to be discovered, one piece at a time.
Right, so to talk about this journey in a smart way, we all need to be on the same page. AI researchers use a few key terms to describe all the moving parts of the search process, and once you get these, I promise, everything else is going to click right into place. This is really the grammar of how AI solves problems.
Okay, so this is a really important but kind of subtle difference, a state versus a node. A state is just a plain fact about the world. I am in the city of Sibiu. That's it. Simple. But an AI algorithm needs a whole lot more to work with, and that's where the node comes in. A node is like a detailed entry in a travel diary. Of course, it contains the state, where you are, but it also includes the path cost, which tells you how long or how much fuel it took to get there. And this is absolutely critical, it has a parent pointer, which is really just a fancy way of saying it has a link back to the node it came from. This is so important because that's how the AI can ultimately trace its steps all the way backward to show you the final winning route from the very beginning to the very end.
And that brings us to maybe the most active, dynamic part of this whole thing, the frontier. I want you to imagine you're exploring a totally dark forest with just a flashlight. The frontier is the very edge of that circle of light. It's the collection of all the places you could take your next step. In an AI search, the frontier is exactly that. It's the set of all the leaf nodes. Those are the nodes at the very, very edge of your exploration that you found, but you haven't yet explored from. The whole intelligence of a search algorithm, all of it, just boils down to one simple repeated question. Which node on this ever-changing frontier should I explore next? So if different algorithms are really just different strategies for picking that next node from the frontier,
how do we know which strategy is actually the best one? I mean, we can't just say one feels faster or seems better. We need a proper scientific way to compare them. And for that, computer scientists rely on 4 key metrics.
To judge any search algorithm, we use these 4 big tests. First up, completeness. Is it guaranteed to actually find an answer if one even exists? An incomplete algorithm is like a GPS that might just give up and say, I don't know, even when there's a perfectly good road right there. Second, we have optimality. Does it find the best answer, the shortest, the fastest, the absolute cheapest route? Some really fast algorithms might find you a solution, but it could be a ridiculously long and winding one. Third is time complexity. How long does it take? And we don't measure this in minutes or seconds, we measure it in how many nodes the algorithm has to create and look at. And finally, space complexity. How much computer memory does it need? This is all about how many nodes it has to keep stored in its memory at any one time. And as we're about to see, this one is often the silent killer.
Now, you might be thinking that with all these different strategies and metrics, there must be dozens of wildly different, super complex algorithms, right? But here's the beautiful secret. Almost all of them, from the absolute simplest to the most advanced, are built on the exact same, really elegant foundation. It's like a universal recipe for search. This loop right here, this is the engine of AI search. It's so cool. You start with just one thing, your beginning location, on the frontier. Then, as long as there are still places to explore, you jump into this loop. And then you hit step 2, the magic step. Choose. This is where different algorithms are actually born. Your strategy for choosing changes everything. Are you going to use a first-in, first-out strategy, like a line at the bank? Well, that gives you something called breadth-first search. Or what about a last-in, first-out strategy, like a stack of plates? That gives you depth-first search. Or maybe a smarter strategy like, let's pick the node that looks like it's closest to the goal. That's called a heuristic search. So once you've chosen a node, you check it. If it's not the end, you expand it. You find all the next possible steps, and you just add them back to the frontier. And then you just repeat. Choose, check, expand. It's that simple, but it is so powerful.
But this simple loop has a hidden trap. What if you can go in circles? Imagine your map lets you drive from City A over a bridge, and that bridge takes you right back to City A. Without any kind of memory, a simple algorithm could get stuck in an infinite loop, just going back and forth, forever, never finding the solution that might be just one other turn away. And that's why we need something called a reached list. It's a really simple but absolutely vital checklist of every single state the algorithm has already visited. It just makes sure it doesn't waste precious time and energy exploring the same spot over and over and over again.
And this brings us to the final and, maybe the most practical piece of our puzzle. In the nice, clean, theoretical world of computer science, these algorithms are perfect little things. But out here in the real world, we are always held back by limited time and, more importantly, limited computer memory. And this creates a fundamental tension, a real dilemma.
So here it is, the real-world bottleneck. We almost always fixate on time. How many minutes is this going to take? But the true killer of so many brilliant search algorithms is memory. For really complex problems, the number of possible paths, the number of nodes on that frontier, it doesn't just grow, it grows exponentially. You might explore 10 paths, then 100, then 10,000, then 1,000,000, and then 1,000,000,000. Long before a theoretically optimal algorithm can find the perfect answer, it can completely fill up a computer's memory and just crash. This is the searcher's dilemma. It's this constant battle between finding the absolute best solution versus the physical limits of our machines.
And so we're left with this final, really thought-provoking question. If the algorithm that guarantees the one single best chess move would take 1,000 years and an entire data center's worth of memory to run, is it actually useful, or would you rather have an algorithm that gives you a 99.9% perfect move right here, right now? This is the trade-off that sits at the very heart of practical AI. It's this constant, delicate dance between the quest for perfection and the very real demands of reality. Figuring out exactly where to draw that line, well, that's what makes this whole field so challenging and so incredibly fascinating. Thanks for tuning in.